All right, my name is Celio. I'm a PhD student here at UC Berkeley, and I'm going to talk about a processor that I've been working on called the Berkeley out-of-order machine. Okay, so first of all, what is Boom? Boom is a superscalar out-of-order processor written in our Chisel hardware construction language. Because we wrote it in Chisel, that means it's a synthesizable core. We can put it on an FPGA. We can put this out to a foundry and get a piece of silicon back. It also, Chisel has helped, as Jonsep just demonstrated, it's helped make the design very parameterizable. So Boom isn't a single design. It's really an entire space of different Boom designs, and you can search this space to try and find the best Boom design, but actually you can find really a Pareto optimal curve of best Boom designs, trading off performance and area or power. So this is something that we hope to use as kind of a future platform for architecture research where Boom can be the base design, and maybe you can either use Boom to extend it to do different things, or you can compare Boom to a different microarchitecture. So that's what Boom is. Boom is a work in progress. So I will show some results in this talk, but of course these are preliminary and subject to change, so don't quote me. So we have been talking about some other Berkeley RISC-V processors. At the very low end is the SODOR collection. These are some tiny educational cores. These are things we use to teach our undergrads about RISC-V and Chisel, and it's not meant to really be synthesizable. It's just a toy. Z-Scale is named after the smallest train gauge, but that is a real microcontroller, as we just saw. Rockets, this is our real train. That's actually the real rocket train. A little slower than you'd expect it to be, based on the name. And then hopefully Boom comes in at the big side. So this is kind of our menagerie of RISC-V processors. And of course, we also have many accelerators, or co-processors as well. Okay, so why out of order? You're a pretty smart crowd, so you probably already understand that it's really great for performance for a number of reasons. Number one, it can tolerate variable latencies. If there's a cache miss, we can just execute instructions around that cache miss, and also around the instructions that depend on that cache miss. For the same, using the same mechanisms, if there's any level of instruction level parallelism in your code, even though you wrote it serially and you didn't even know it was there, the out-of-order core is going to find it, and it's going to execute a lot of instructions in parallel. You can also think of out-of-order as a really complicated way to do fine-grained data prefetching. If you know the addresses, we can get that out and start executing them. And for these reasons, out-of-order plays really nicely with terrible compilers and terribly written code, which describes most stuff out there. So, if you're trying to sell a product, you find out that if we really care about performance, we're actually willing to pay the costs and the complexity in doing so. So maybe it's not a surprise then that out-of-order, that industry has kind of converged on out-of-order as being kind of the microarchitecture of choice for these application cores. And that's a bit of a surprise. If we look at, going back 5-10 years, this wasn't the case. People were afraid of power. They thought maybe we had to go back to in-order cores, have a lot more cores for throughput. But it turns out that actually, if we look at something like the PlayStation, that was a multi-core SIMD in-order thing. But it turns out all these processors have now moved on to being out of order. So I think we can, out of order is what the industry has decided is what they're willing to pay the power and complexity for to get that performance. Now, despite the fact that industry has moved towards this, among academics, unfortunately, there's been a general lack of effort in academia to build and evaluate out-of-order cores. There's a few exceptions I'll get to in a second. But in general, for 20 years, people have been using software simulators to evaluate their ideas so that they're not building an out-of-order core, they're building a model of an out-of-order core. And that means that you can't really get any sort of area or power numbers out of this, which is now a first citizen design constraint. And it's really hard to kind of trust and verify the numbers even for performance. It's very easy to describe in a software simulator something that's completely unfeasible. For example, it's very easy to build a branch predictor that's really good that requires a 16-ported SRAM. So you can get yourself in a lot of trouble with the software simulator. And even though that there's tools like McPat that can give you power, you can only really calibrate against a single design, but you're not interested in necessarily always simulating a 90 millimeter Niagara. You want to simulate something that's a little bit different, something maybe off the curve, or maybe search different design spaces. So software simulators, and also really they're also really slow. You'd like to think that if you're training away accuracy, you're at least getting something for it. But in reality, you just really can't even run a full spec program on these. Now there are some other academic efforts. I can count them on one hand. Now, looking at some of the past research, Illinois and Princeton were using a subset of the alpha ISA. FabScalar is using a subset of the PISA ISA. These are still, projects that are, in progress and still evolving and changing. However, looking at the past work, you find out that it's really hard to actually build a full ISA. Did you get all the condition stuff with the integer? Did you get the floating point? Did you get all the multi-core primitives with, atomics? Do you have the privilege spec? Do you have the platform spec? There's a lot of things that are really hard that just aren't worth the time to research interesting ideas. So with Illinois, for example, they were interested in studying transient fault detection, so they wanted to be a latch-accurate model that they could inject faults into and then maybe come up with microarchitectural ways of detecting and correcting those faults. They didn't need to necessarily, boot Linux or anything. The other thing is that, so far, people are still relying on software simulators to get their performance numbers. So they have the RTL that they can get a lot of cool data from, but for performance, they're still relying, for a lot of really good reasons, on a software simulator. So number one, software simulator is slow, but the RTL simulation is even slower. And number two, the software simulator can support a lot more of the ISA and the platform than the RTL usually can, so you can still run more programs than you could. However, we're kind of hoping that RISC-V can make everybody's lives easier in this respect, that we can make it much more tractable for academics to be able to build the entire system. So just kind of as a motivation, this is here's the design space we want to be able to explore. We want to be able to have, performance on one axis and area on the other. And, you want to, in this case, this is just very preliminary. We're changing some of our parameters that we can change. And, you get a nice Pareto curve where there's actually a trade-off between performance and area. And, this is just a simple task where we're just kind of randomly picking points. But you can actually get a 3x range in area and a 2x range in performance. So this is actual real preliminary boom data. Now, of course, we want to use something much more, elaborate than CoreMark, but, which benchmarks do we want to use, and how many cycles do we want to run? So I was looking at what the state-of-the-art is, and state-of-the-art is use SimPoint, so this is a tool that tells you which are the most interesting points of an application to run. And people tend to run about 4 or 10 of these snapshots on Spec 2000, 2006, and they run each for about 10 to maybe 100 million cycles. So I looked at, ISCA 2014, this is, the International Conference of Computer Architecture, and I was seeing that they're running about 50 million instructions per workload. That's 200 billion instructions per paper, if you count that up. So what do we hope that we can do? So we're going to map our design in FPGA. We can run at 50 megahertz. That's about 1 trillion instructions, or 1 trillion cycles, rather, in 6 hours. And just to give you a reference, if you want to run a single spec reference 2006 benchmark, you're looking at around average 2 trillion instructions to do that. So if we have an FPGA cluster, we could actually in a single day run 30 to 60 trillion instructions a day. So we're hoping that maybe we can actually get you like a spec number, which would be really pretty cool. So before I talk about what Boom is, I want to talk about some of the infrastructure at Berkeley that's helped enable us to be able to build something like Boom. Our RISC-V ISA, our Chisel hardware construction language, and our rocket chip SoC generator. So starting with RISC-V, turns out it's really easy to implement. This is something people don't think about when you think about an ISA, but how is the memory model? It turns out that has a dramatic effect on how you build a load store unit. If it's a sequential consistency that's demanded, that means if another core has a coherence traffic come in, that probe has to search the load store queue. So that's, something like a relaxed memory model can really simplify design. We accrue floating point exception flags. Not all ISAs do that. Some demand that you actually, same with integer side effects, they demand that you know what the condition code of all the previous instructions were. At any given instruction, you have to know what the last one was, which means that you have to rename all that state. In this case, if you just accrue it, you just OR things in at commit time. There's no C-mover predication. There's also no implicit register specifier, so even something like a jump, you have to specify that you actually want it to go to the return address. And also, the registers are always in the same place. And those last 2 points means that you can do decode and rename in parallel. You can actually just look at the instruction bits and throw that to the rename tables. You don't actually know what instruction it is. It doesn't matter. You can still get that in flight. So that allows us to have very short pipelines. It's pretty cool. Now, of course, I have to mention RVC, the RISC-V extension. That does relax some of the implicit register specifiers, and some of the times they move. So, I guess we call it the compressed extension, but you could also maybe think of it as the RISC-V CISC extension. But on the counterpoint, it does expand into the regular RISC-V base ISA. So you add maybe a little bit of FO4 on the critical path, but it's still a very simple ISA. It doesn't affect the back end. So Boom supports M, and you can change whether your multiplier is pipelined or unpipelined. I support A, all the atomics, load reserve, store condition, and I support F and D. So we're talking, single and double permission FMAs, along with hardware support for subnormals. So this is not true last retreat, but this is now true now. So I implement all of RV64G, which is really pretty cool. If the compiler spits it out, I can run it. I also heavily rely on the Rocket Ship SoC generator. This is open source. You can use it now. We've taped it out 10 times at Berkeley, and we've demonstrated running at least 1.6 gigahertz in IBM 45. From my point of view, this is an awesome library of processor components. So there's the Rocket Ship up there, and I've basically made sure that Boom is essentially socket compatible with Rocket. So I can swap out Rocket for Boom, and suddenly I have a Boom chip SoC generator. I get all the caches, I get the memory systems, I get the cache coherent stuff, I get all the tool chains, the tool flows. So for me, this is really a huge gain. Boom also supports the privileged ISA, the latest one, 1.7. It also supports virtual memory, which means I can actually boot Linux. And not just like canon the theoretical, like I've actually demonstrated it, gotten a command prompt, and I've never been so excited in my life to see a command prompt show up. And what's also nice is that anytime that we update the privileged ISA, we make those changes into Rocket's, the CSR control file. To me, that's just a submodule pointer in Git, so I get to update that. Maybe if he changes the name of toHost, I'd change that, but I get all this for free. This is really, really awesome for my productivity. And Unsup, I think, has helped sell Chisel pretty well. For me, this allows me to describe very highly parameterized designs. So as an example, I was trying to run specint, and I found out that specint has a lot of floating point in it. I didn't expect that. It turns out that even if you only have 1% of the program is floating point, but it takes 100 instructions to implement a single floating point instruction, that means half your time is spent doing floating point. So I figured, all right, fine, I'll bite the bullet, I'll add floating point. It took me 12 days to do that and 1,000 lines of code in Chisel to go from absolutely only an integer core to renaming the register file, the function units. Now I'm able to leverage existing hard float units. I'm able to leverage the existing stuff that Rocket had, but to add all of that infrastructure, all the speculation stuff to Boom, that was 12 days. Another design point was it took me 9 days to go from no virtual memory to being able to boot Linux. I was able to leverage Rocket's page table walker, their MMUs, their connections to memory system, but I did have to rewrite the load store unit. I had to hook up all this stuff and make sure that Boom could understand all of this. Make sure that you're not forwarding a store to a load. You have to make sure that's a physical address. But that only took me 9 days. Okay, so let's talk about Boom now. This is at the very, very high level of what Boom looks like. So we're going to fetch instructions, put that in fetch buffer. We're then going to decode each instruction and rename that to give it a new physical register. And then those instructions are going to go into the issue window. When they're ready, they're going to request. We'll select from the requesters. And then when they execute, they're going to read their operands from their register file, execute, and then write back immediately. So the front half is in order, and then at the issue window is when we're going to start issuing out of order. So if we dive in just a little bit more, this is an explicit renamed design with the physical register file. This is holding both the speculative and committed data. The map tables are what tells you what's actually the committed state in this. This holds both the integer and the floating point registers. So you can just think of an FPU as like another functional unit. And the issue window is going to hold all instructions, branches, memory ops, floating point integer. So there's different designs. There's different choices you can make in a design, but these are the choices that I've made. Boom is a parameterized superscalar. So this is this is a dual issue. So this is ALU floating point integer multiplier. Here's the other side with the load store unit and a divider. And that actually is 3 lines of code. So the execution units is an array buffer, and I just do plus equal, instantiate a new module, and tell it what function units it has. And if I want the second unit, I just do another plus equals, instantiate a new thing. So to go from a 2 issue to a 4 issue is just another 2 lines of code. That's pretty awesome. And just to explain what's going on here, each of these modules that I'm instantiating is a new one of these things, but in Chisel in my code, it's parameterized such that each one of these things adds another write-back port, it adds another read-back port, all these bypasses generate a bypass network, it adds the issue select logic, it adds the wake-up logic. All of that stuff is essentially auto-generated just based on doing another execution units plus equals instantiate a new module. So this is really powerful. I have full control over the issue with and the function unit mix of this design. I do full branch speculation. I have a next line predictor with BTB, return address stack, a combination of G-share in there so I can predict without bubbles. I also have a larger backing predictor implemented in SRAM. This gray box, this is all Rocket code. So I'm actually getting to steal all of the effort in terms of the iCache, the next line predictor, the virtual memory. I get all that for free. So that's pretty nice. Anytime we update that, I get that. The load store unit, this is a textbook load store unit. It has store ordering, so that means a load can execute fully out of order with other loads as well as other stores. And if a load depends on a store, then that data gets forwarded pretty aggressively. So this is just a textbook standard load store unit. And it's connected to a non-blocking cache that, again, that's the same cache that Rocket uses. I get that work for free. Boom is synthesizable. We can run this on an FPGA. Our tape outs with Rocket have been going at 1.5 gigahertz, so I'm just trying to make sure that I'm at least faster than that. So if they tape me out, I'm not the slowest thing. So if I were to make, SRAM, this is through synthesis, if I make the SRAM as fast as possible, the logic goes about 2 gigahertz. So that's what I'm trying to aim for. And what's really neat is that this took 9,000 lines of code in the Boom repository, and there's an additional 11,500 lines that I'm taking from other people. So that's function units, caches, page table walkers, coherent stuff, floating point. It's a lot of stuff that I get to use. So 9,000 lines of code, I've heard somewhere before that about 10,000, 15,000 is what you can hold in your head as a single programmer. So this is something that, one person can understand, which is pretty cool. And as a summary of the Boom features, this is, again, the full RISC-V RV64 ISA, synthesizable on an FPGA, parameterized, floating point ammos, caches, virtual memory, can boot Linux, and with the Rocket Ship SoC generator, you can easily make this multi-core, and it understands that. And it was 9,000 lines of Boom code, 11,000 lines of Rocket SoC code. So that's what Boom is. Now, you might ask, okay, what is the quality of this design? So I had an ARM core lying around in lab, an ARM Cortex A9. This is a little bit older design, but it turns out that they still ship this. You can still buy this and put this in products. We actually just got some new ZC706 boards that happen to have an A9 in it. So I said, okay, let's give this a try. This is a 32-bit ARM, which means that the register file is going to be half the size as mine. But I did pick a Boom design that would match ARM as best as I could. So it's 2-wide Boom, 3 issue. Again, it's a pretty short pipeline, so 6 stages. And it turns out that I was 9% better on CoreMark, which was pretty cool. CoreMark is what ARM uses to brag about their design, so I figured, okay, I'll play in their arena. And if we put this at 40 nanometers, it's very hard to kind of figure out what area actually is with Boom. And putting this through Cacti to generate an SRAM model for the caches. For the A9, it's a bit hard to find that number. Obviously, it depends. I found something that probably shouldn't have been indexed by Google that gave me a die area and a die photo, and then I could count the pixels, and it looked like about 2.5 millimeters squared. That number can change by about 30% based on whether you're going for performance or for power. So that's certainly a number that's fungible. And if we look at area efficiency, Boom's looking pretty good. And we're actually both targeting the same frequency. So it's not like, the CoreMark per megahertz is a false comparison here. So I thought that was pretty cool. Not bad for 9,000 lines of code. Okay, so how does it compare against other processors? So I had a few other stuff lying around the lab or things I could find on the internet. So the Ivy Bridge, so these are color-coded based on company. So we have blue is Intel, green is ARM, and Berkeley is in gold. So we have Rocket doing pretty well against a single-issue in-order core. This is a dual-issue in-order core. So these are just, these are, Boom 2-wide and Boom 4-wide were just, 2 Booms that I kind of picked that seemed to kind of match an A9 and an A15. And so I was able to match those performance in terms of CoreMark per megahertz. The Cortex A15 is designed to be very highly pipelined, but usually when it's actually implemented, it only ever runs, about 1 to 1.5 gigahertz usually, but it can go up to 2. Now, if we look at that same data, but with, say, bringing area into this, and this is assuming perfect scaling, of course, but if we perfectly scale from 45 to 22, the Intel core is 48 times the size of Boom. So, not bad. I hope their CoreMark score is pretty good. And if we want to look at an Ivy Bridge tile, this is with the L1s and the L2s. And we compare it to a boom with the same L1s and the L2s. This is about the size at 45 versus 22. And if we were, again, to perfectly scale boom down to 22, this is what boom looks like. So, go and look for the branch predictor, and I think that's probably about the size of it. And again, we can do some really cool things with boom. We can get, synthesis results. So we can, here's Rocket with no FPU. Here's Rocket with an FPU. We can kind of see what the costs are as we, scale boom up to hit different design points. If we look at, caches, it turns out, the difference of a floating point unit is kind of in the noise once you add caches into this, at least for Rocket. So we can do some pretty cool stuff with this. So I want to talk about, end with some lessons. Turns out RISC-V is a really great ISA. It gets out of your way. And in terms of performance, it's competitive against the other industry ISAs. So I found out that the instruction counts across different GCC versions varied much bigger than across ISA. So at CoreMark, ARM, x86, RISC-V were a few % difference. RISC-V winning some of those. But if I wanted to go from, say, ARM, ARM brags about CoreMark scores, right? So you'd think that if there's one program GCC can do really well with its CoreMark, GCC 4.6 to 4.9 was an over 50% improvement in CoreMark score for an ARM core. So that means that instead of buying the new A15, you should just use an A9 with GCC 4.1 or 4.9. So RISC-V is pretty good. Code reuse is really great. It's been very nice to be able to leverage all the existing stuff at Berkeley. Benchmarks are a real pain in the butt to deal with as an academic, so we should share our efforts. In terms of spec, I put up a little GitHub wrapper, so if you have spec really kind of assumes that you are going to run natively on a machine, not under a simulator or on a FPGA or something, so I put that up there so that way we can maybe share those efforts. And debugging is really hard, it turns out. Good verification tests are way more valuable than good RTL, and it'd be great if we could kind of share our efforts on this front as well to be able to share, test suites and torture testers. And I learned I should really use the certs everywhere. It's a little embarrassing to go back 2 years and realize how much you rely on just getting the correct answer at the end of it instead of trying to catch the errors early on. Boom implements the full ISA, including the privilege spec. We can boot Linux, run CoreMark, SpecInt, and Drystone. Boom is 9,000 lines of code and 3 person-years of work. And in terms of future work, obviously I want to bring up some more interesting things than just CoreMark and spec. I am going to add the ROC interface so we can communicate with our accelerator stuff. And I do want to, I'm pretty happy with where Boom is right now, but I do want to explore some new designs, maybe tape out this fall, and open source by winter. So thank you.
Why take so long to open it?
What?
Why take so long to open it?
Okay, so unfortunately, I'd really hate to get scooped by my own processor in terms of research. So I'm pretty happy with where the design is now, but I still have to publish something with it, and that would be really kind of silly. So I'm hoping to get some stuff out in flight this fall, and then publish it in the winter.
Peter Shu, Oracle Labs. Is there any prospect of integrating with the people working on the vector unit?
Yeah, I am interested in adding the ROC interface, so that way we can communicate with the Watcha vector unit and any other vector units that they make or other accelerators. So that is something that's on my to-do list, is to be able to integrate with that. And that would be, you're talking to an in-order accelerator, so you have to send things at the commit time, or at least once you know things aren't committed. So it's maybe not the optimal design of how you would do V extension, but that is something that I'd like to do. Yeah.
So what about a fully integrated out-of-order?
So the question is, what about a fully integrated out-of-order vector machine? Out-of-order V extension. It's certainly something we've talked about, something I'd be interested in doing, but it's not on the immediate plan. Does Jensop have a comment he wants to make? Here you go.
Yeah, but, wow. So there's a little bit more consideration you need to do if you want to integrate the V extension in an out-of-order processor. Like, are you going to rename the vector registers? Like, how does predication all work out and things like that? You know, we definitely had discussions about it. And Hwacha is more suited to pushing in-order designs to its limit. So I think the microarchitecture, unfortunately, if you want a high-performance out-of-order V extension, it would need some more architecting and microarchitecting, but we can definitely talk about that. I mean, we've been talking about that for years.
Oh, I'm Trivikram from Google.
Which slide do you want?
You know, the one where you showed that you had to add only 2 lines of code for making it 2 wide to 4 wide, something like that. Yeah. So I guess I have 2 questions. One is, is the starting point here still the rocket chip generator, or you had a different chip generator?
Yeah, so rocket chip is, so that's like a whole SoC, a whole computer. And so basically what I'm doing is, instead of instantiating rocket, there's a function literally that like returns a processor, and that function returns boom in my case. Like it's like a single flag that returns a boom tile. So I'm fitting within the rocket SoC. However, I'm also instantiating code in the rocket chip repository. So it's kind of like it's like a library from Boom's point of view, if that makes sense.
Okay, I guess my question was, you know, in a typical out-of-order processor, if you went from 2 wide to 4 wide, something like that, or 2 issue to 4 issue, there are a host of questions that come up. You know, how does the picker work? Do you look at the 4 oldest, or do you cut corners there, and all of that? And can you speak a little bit more to, you know, whether the chip generator handles that in a parameterized fashion, and if so, how does it handle these kind of questions?
How does it handle?
Could you say it again a bit more clearly?
Oh, so my question was, you know, if you go from a 2 wide to a 4 wide architecture in a traditional flow, you have to handle a lot of fundamental questions around meeting timing, and you cut a lot of corners, because as an example, you know, if you wanted to pick ready instructions from the scheduler, and if it were a 2 wide out-of-order machine, you might be able to pick the oldest 2 ready. But if you were a 4 issue machine, it's usually pretty hard to do a 4.
Okay, right.
Right. So how do you handle those questions in a chip generator context?
Right. So when we have a chip generator, you can only verify what comes out of the generator. You don't try and verify earlier. So in terms of something like the clock frequency, I'll pick a design, throw it through, and hit on the critical path. So right now, I've been paying most attention to the dual issue, making sure that that runs pretty decent. The 4 issue, I've not had enough time. That's not going to run at 2 gigahertz. But typically, you know, the SRAMs are pretty slow, so you can hide a lot of logic. But yeah, if you do 4 wide, there's other things that you might have to shrink in size. The issue scheduler is parameterized. You can change between whether you have an age-ordered collapsing queue or an unordered, you know, R10K design. So if you do find that there's some things that, you know, you paid for in one area, you can change a parameter to change for it in another area. But yeah, you'd have to kind of, you know, the clock frequency is going to be, you know, different between different designs depending upon how aggressive you are.
This is Jenny Zhang from LG. You compare the boom and ARM performance gain and area much smaller. How about the power?
Power is an excellent question. That is an ongoing research topic, and we have some other students that have some really interesting ideas of how to get power out of simulation. But yeah, that's a challenging question, so I don't have any.
Yeah, we actually need to run the detailed numbers, but I think to first order, the area is a good proxy for power at the same clock rate. Start, you know, give or take. Most SoC designers kind of, you know, equally clock gated kind of designs done at the same frequency. You're going to roughly, you know, you should take that as a proxy for the power. The other cores that we've done the power comparison on, it's sort of in the same range, you know, give or take.
But we do want to be able to answer that question. That's a great question.
You said simulator is fast enough, then, well, is it cycle accurate simulator?
So all my results are done using the RTL. So Chisel generates either you can generate to ASIC Verilog, you can generate to FPGA Verilog, or you can generate a one-to-one exact copy of the RTL but running in C++. So You know, it's just like running an RTL simulation, except we had a few tricks to make Chisel C++ run really fast. So that's not a model that's the exact cycle accurate. You can poke any individual wire or register and see the value of it.
Then what about the performance if it is compared to other tools such as Verilator or some DPI functions or something else?
Right, so when we started Chisel, I think Verilator was not in a good place. And so for what our simulations were, the C++ that Chisel generates, in part because it's two-state and in part because it's not an action queue, it's a straight flow through the diagram, our Chisel C++ is really fast. We are interested in kind of reevaluating that decision now that Verilator is a much more serious contender. But I don't have a comparison of Verilator versus C++.
Okay.